Um, Good afternoon to everyone. I welcome all of you to the 42nd lecture in the lecture series in Nonlinear Dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from RUSA 2.0. It is my pleasure to introduce you today's speaker, Dr. Jyoti Prasad Saha from Department of Physics, University of Kalyani, Kolkata. Professor Saha did his PhD in Jawadhpur University, Kolkata, and carried out postdoctoral studies at Institute of Mathematical Sciences, Chennai. He started his career as an assistant professor in Banaras Christian College and then moved to University of Kalyani in the year 2010. Since then, he is working in the University of Kalyani. Professor Saha is working on different areas of physics, including quantum field theory, theoretical particle physics, general relativity, and quantum physics. I think he has been invited to give several lectures in particle physics. Today, he is going to talk about coherent states, which will be very useful to the graduate students. With this short introduction, now we invite Professor Saha to deliver his lecture. Over to you, sir.
Thank you very much, Professor Sentivelam. It's my pleasure to give a talk in front of you people, and I am just starting to learn about those field coherent states and all those things. So I am really novice, but as you told me to prepare the talk for the students, so I am just prepare my talk, whatever I learned, and I think the talk would help me to learn more things because you have some other so many expertise in that expert in this field. So I think I may gather some knowledge from this talk. So thank you. May I start now?
Yes, sir. Yes.
Okay. So the screen sharing done already?
No, we are not able to see the slide.
Okay, I just yeah.
Yeah.
Now, if people,
Yes.
okay. Okay, so the talk is mainly prepared for the students, not only the students. It's also based on our recent work, or mainly the work done by Kalpana Vishwas, I mean PhD thesis. So I am not at all expert on that particular field, but I gathered some knowledge. So I wish to share with you people. So the talk I already named as the coherent state and its construction mechanism for different physical situations. So what I will try to do that I give some motivation for choosing this coherent state for my future studies and all those things. And then what is the coherent state and how can we prepare a construct a coherent state in case of different physical situation. So I mainly concentrate about the some sort of what is coherent state, and then try to tell you some the construction mechanism, basically two mechanism, and then I'm telling some and some different example also. So start with the outline is my talk is why do I want to know this topic? Means it's as this basically I'm preparing for this for students, so I'm presenting my talk in that way. Why it's basically necessary to know this type of things, and then obvious thing is the some knowledge. Now it's on the textbook and it's a very easy to calculate what is the coherent state and some information about the squeeze states and why we need Wagner measure, Wagner distribution functions. And then the construction part, when we try to establish two type of mechanism. One is called SUSY quantum mechanics, and another one is the position dependent effective, another is Lewis-Risenfeld invariant method. And in between that, I am picking a example to stress that particular example is little bit more. It's on the position dependent effective mass system, and that's all about my talk. But I think it will take 50 minutes or something like that. So it's okay, I think so. So why I want to know this topic? So this is actually the question. And now whatever I am showing, the slide content so many things written in it, as because in my opinion the talk is always in front of some student. So it's better to talk offline than online, as then the attachment is basically established. So as I am giving my talk in online, so I think to write all those things in my slide, so that in any kind of noise or any kind of disconnection between me and you, then at least you people can see the things what I'm trying to give or I'm trying to tell. Oh no, not again. It's because I'm writing this because the talk. I mean, my opinion, listening of some talk is sometimes bored me. So whenever people give a talk, they always give some motivation behind it, and that's why it's my feeling is, oh, not again. But still, I am doing so because I'm telling about coherent state and the construction of coherent state. So why we pick this particular thing? Because now you people already have gathered so many knowledges, and I mean, you people are now knowledgeable persons. So you know that our daily life experience needs a classical mechanics, which is support our human civilization, and the deterministic approach, it basically the attitude even can utilize to determine the dynamics of space time. But you already know that the some kind of experiment suggests that nature is quantum mechanical, according to which randomness is there. So theory and experiment both their suitable validity range, and believe that there must be some connection in between the classical and quantum domain. So that's why when we think that there is some measurement uncertainty, but classically measured quantity is perfectly accurate measurement. But when we deal with quantum mechanics, there is some measurement uncertainty. So the best way to connect these two things is if we lower down our measurement uncertainties, so that might be helpful for us to find out a quantum state which are closely resemble to the classical states. That's why we just go through this particular thing. It's more or less the main motivation, but still I tell something to you, that as there are some non-commutable observable in quantum mechanics, we have to find out some state which minimize the measurement uncertainty. And this is the goal. So classical particles are localized in space, and we find out the quantum state, which is the probability density, are highly localized. And already this ground state of harmonic oscillator fulfills almost this criteria. And this ground state of oscillator, harmonic oscillator ground state, is also the eigenstate of annihilation operator, which I already people know that. And these things in connection with the optical coherence and harmonic oscillator eigenmodes. I am not telling these things in a detail, but still I am just pointing out this point. This connection with the optical coherence and the harmonic oscillator eigenmodes, Glauber and Sudarshan has adopted the name coherent state for the eigenstate of annihilation operator. So those are the reason behind study of the coherent state. We are just trying to connect the classical and quantum things in a manner that we can straightforward go to one to another, but it's so much easy. But still, if we have a state which has minimum uncertainties, then we can do these things. So keep it back of the mind, and we start our journey. So our main point is consider the notion of coherent state as eigenstate of annihilation operator. AO stands for the annihilation operator, and try to develop the notion of coherent state for some different physical situation. And then after that, we are trying to give you some idea about not only the coherent state, give you some idea about the squeeze state also, and then some different things, which is very important thing, the Wagner distribution. And then I'll go to the construction mechanism, which is basically divided into two parts: the SUSY mechanism, SUSY quantum mechanics formalism, and LRI method, means Lewis-Risenfeld invariant method. And I am telling you a specific example with a little bit effort or little bit stress, that is called position dependent effective mass problem. It's basically, you can I'm writing these things, basically I'm trying to tell you SUSY and LRI, so I am basically give you an offer that buy two get one free. So SUSY and LRI, and some little bit on position dependent effective mass problems. So now, coherent state. So as we already know and already go through all the calculations, so I am not waste my time very much on that particular part, but I am just pointing out the properties and the points on coherent state, and you can do the calculation by yourself. It's very much available in all the literature books and the internet also. So many articles are there. So in 1926, Schrödinger first gave the idea of coherent state for a simple harmonic oscillator. And then after that, a long period back, Roy and J. Glauber got 2005 Nobel Prize for his contribution of quantum theory optical coherence. So I'm not going through in that part, but just the point I mentioned, that coherent states for a laser beam is basically tell us that there is an indefinite number of photons, but a precisely defined phase. Whereas in case of the non-coherent state, particle number is fixed, but the phase is completely random. So there might be an uncertainty, which is in between the occupation number, or you can say that amplitude, and the phase part for the state, and which must be a minimum for coherent states. And that is basically given by delta n into delta phi is greater than equal to half, and minimum is equal to half for the coherent state. So the coherent state is termed as Glauber state, and it is defined as the eigenstate of annihilation operator. And this annihilation operator is not anymore Hermitian operator, so the alpha is a complex number, so basically associated with a complex phase. Now, vacuum state for harmonic oscillator is also a coherent state with eigenvalue alpha equal to 0. We know that the vacuum state, if we operate the annihilation operator, or you can say the lowering operator in the ground state, it gives you 0. So the eigenvalue is 0. And if you calculate those are the properties. So in detail, you can calculate those things, but I am just telling you the fact. So if you calculate the mean energy in case of the coherent state, for the coherent state, you get some result like h cut omega alpha mod square plus half. So this h cut omega alpha mod square is basically the classical wave intensity. So it very much resembles with classical mechanics. So now the another things which can give you a coherent state when you act that particular operator on the ground state, we get a coherent state, but that's called a displacement operator, and whatever we get is called a displacement coherent state. So ground state is also a coherent state, but when we apply a displacement operator, it gives you a state which is not a ground state but a coherent state. This is the picture of that thing. So this is the ground state, and this is basically the due to the displacement operator what we get here a coherent state, and this also a minimum uncertainty state. And as I already mentioned, that we need a localized probability, so coherent state also gives that thing. Many other properties. If we calculate the structure of coherent state, what it looks like in Fock space, then we get this result. It's a very easy calculation. And then the probability distribution for coherent state, you can calculate these things. This gives you an idea that the alpha square, I can change it to the mean photon number. So classical particles obey the same statistical law of Poisson formula, and the photons in a coherent state, they behave like randomly distributed classical particles. And the another thing of coherent state is is not orthogonal state. If you do the calculation for a alpha state and beta state, then you get e to the power of something which is not 0, but it's 0 can be 0 for the alpha and beta. Difference is much less than 1. The completeness relation, which for a coherent state is written like this, so it gives you an idea that it's a over complete state. The coherent states are over complete state, because we already know that the completeness relation gives only the integration over something is equal to 1, but it has have a factor, so it's an over complete state, and it means the coherent state can be expanded in terms of all other coherent states, but is not linearly independent. Now, the bottom line is coherent states are minimally uncertainty wave packets which remain minimal under the time evolution. That part you also I think you people already did. If you do the calculation of time evolution for a coherent state, then it remains coherent. So the minimal uncertainty is also there. So time dependent, when we do the time evolution part, the time dependent expectation value of x and p satisfy a classical equation. Renthus theorem gives me that things. So the coherent states are very natural for studying the classical limit of quantum mechanics. So those are the motivational facts. I think you people already go through it, or you not, then please do the things. You have so many books and articles are there. And the most interesting thing is calculation are not bad enough. It's good, means you can do the calculation by yourself. So these are basically an image of a coherent state. I'm picking from the internet, and I can these things you can say that the time evolution of coherent state remain coherent when we both evaluate it under time. So that's all about the coherent state, and it gives idea that whenever you consider a coherent state, basically fill up almost 3 criteria. One is it should be a eigenfunction of the annihilation operator, and the another one is the time evolution of coherent state keeps the coherent state remain coherent, and another thing is the coherent state time evolution operator of coherent state that keeps the coherent state remain coherent, and another thing, the minimal uncertainty state. Coherent state should be the minimal uncertainty state. So in keep of the mind is those three things. We can proceed further. So before going into that, if you want to squeeze the state in a way that it gives same uncertainty relation, means the uncertainty remain minimum, but you can squeeze the state in such a way that any of the variable in between the two conjugate variables give you the uncertainty less than the actual one. So what I'm trying to tell that I'm just telling you. So actually the uncertainty principle is the area on the phase space. It basically is the product of delta x and delta p type of thing. So area of the phase space. So squeezing the area does not mean we can devalidate the uncertainty principle. So why we need these things? Some type of optical communication problems, someone wants to minimize the uncertainty in one of the two conjugate variables. But he or she can't do this job without hampering the minimum uncertainty things. So it can be done. So it is possible to find a state which have minimum uncertainty at the expense of a larger uncertainty in the other conjugate variable, so that the product remain the fixed. So can we do that? Yes, we can do that. And this is called the squeeze state. So consider two conjugate non-commuting operator A and B, just like our X and P, and A and B satisfy the commutation relation, which is they don't commute, and C is another Hermitian operator. And if we calculate the delta N and delta B, the expectation, the values comes out to be the expectation value of the another operator C, and this is minimum for the uncertainty states, suppose psi. Now the state is called squeeze state when one of the observable means delta A or delta B less than this half of the C, expectation value of modulus of C. But the delta A and delta B product remain the minimum, means half module absolute value of the expectation value. So if any one quantity, any one of the variables, the delta A or delta B, means if you lower down the uncertainty on that things, then you have to be raise the uncertainty on the other conjugate variable so that the product remain constant or minimum. The squeeze state follows these two things, means any one of the conjugate variables, the uncertainty of that follows these things, but along with the uncertainty minimum thing. So what do you mean by squeeze state? The squeeze state basically offers you the possibilities of beating the quantum uncertainty limit in measurement. One thing is clear, it is not the Fock space, our well-known Fock space N, and not the coherent state, but we can produce a squeeze state by using the squeezed operator, which looks like S size type of these things, and it is a function of A and A square and A dagger square, means the creation and annihilation operator square term. And if you act that particular squeezing operator on the ground state, you get a squeezed ground state. And if you act these things on a coherent state, you get a squeezed coherent state. So you can get the squeezed coherent state in this way, that you first act the squeeze operator in the ground state, and you ended with a squeezed ground state, and then do the displacement, operate the displacement operator, and you have the squeezed coherent state. So this is the more or less the picture or pictorial representation of squeeze states and coherent state. If you look at this thing, this is the vacuum, a coherent vacuum, and now I operate this thing. Now I operate squeezed operator in that particular thing, so it basically gives you the squeezed vacuum. And now if you apply a displacement operator in this ground state, then you get the coherent state, and then you squeezed it and you get the squeezed coherent state. Now I'm giving this picture because of you can squeeze your normal harmonic oscillator in that way. That is the dark line is the old harmonic oscillator potential, and the light dark line is basically gives you the potential of squeezed harmonic oscillator. So the ground state, the dotted one, is basically the dark one is basically my squeezed ground state, and it's original ground state, and the dotted one, I think dotted one is basically my squeezed ground state. So now there are so many possibilities for squeezing the things. You can squeeze it in a phase squeeze way to give you phase squeezed state. If you squeeze the amplitude part, then you get the amplitude squeeze state. And this is a picture where we show that how the light squeeze state can be formed. So this is a coherent state of light, and if you squeeze the phase part, then you get that type of picture. And if you squeeze the amplitude part, then it's basically gives you this thing. And the vacuum state, if this is the thing, then after squeezing it, it gives you a picture like this. So now, the other thing I am now telling you that not in detail, but just some idea that we need some different type of things, but different type of representation, which basically connect me to the classical picture, from the quantum to classical picture. As we already know that this harmonic oscillator, Schrodinger, the equation is only one variable equation. So we need a phase space type of construction so that I can easily manage to communicate from classical and coherent things. So we need a Wigner distribution function, which is basically a function involving space and momentum, both the things. And this is the Wigner function in phase space distribution. Now, if we find out that particular coherent state and then do that particular, and then do it and then dump it in that particular equation and find out that psi, it gives you a distribution which is called Wigner function distribution. And in classically, if you look at it classically, then Wigner distribution function is not positive at all. But when in pure state, or in the pure state of psi, it's positive definite, but in classical mechanics actually. But when we do that thing in place of our quantum mechanical scenario, it gives some negative indication or negative things, which is basically the quantumness of the system. So the judge the quantumness of the system, you need that particular Wigner distribution thing. So it is a very good way to judge whether there is a quantumness still there or not at all. Now, this is the Wigner distribution thing for harmonic oscillator. It's a good one. You can do these things, but I'm trying to concentrate in that particular diagram. I'm not going into the detail, but these things gives you an idea that if I'm trying to do the thing, means I'm trying to do a work that I'm just two particles there, positive spin or negative plus of spin or minus spin. I'm just displaced in opposite way, opposite direction, and then calculate all those things and Wigner distribution function, and it gives you a distribution like this. And the middle portion, it shows the quantumness of the system. This is doing for a cat state, because the middle portion is always means here. But if the state is coherent, means then we can we get minimum quantumness things. Means this part is almost minimized. So when we act on the coherent state, we can say that this distribution is good enough. There is almost minimum quantumness, but other than the coherent state, you can get this negative things, which totally unlikely for classical mechanics. And this negative distribution things gives you the quantumness of the problem. Now I come to the point of the construction mechanism of coherent state. So mainly I am doing these things in a two-way. One is the Sushi formalism and another is the Lewis-Risenfeld invariant method formalism. So first I am telling you about the Sushi formalism. So you have already, you do these things in your well-known harmonic oscillator problem. The Sushi formalism is basically done with those Hamiltonian, or you can those for those system which is time independent. Uh, uh, Means you can have equation like H psi equal to E psi type of thing. So and also you have p square and the quadratic term of momentum and also quadratic term of position, so that you can factorize these things. But the factorization, you can do this factorization in that way that you just think that it is your Hamiltonian, looks like a pretty similar with our well-known Hamiltonian, and we can construct annihilation and creation operator. We keep in mind that Wx is a real valued function, and we just do the factorization. Here W is the superpotential, so we have to calculate this superpotential. Now what we do, we just finally formulate that H in terms of A dagger, and we demand that H should be A dagger type of thing. So whatever things may come out with W, we can simply attach it with V, and we get a Riccati type of equation of superpotential. This Vx is our old Vx, and now we have an equation of Wx, and solving this equation we can get our well-known W, and we can also formulate the annihilation operator. And after that, the annihilation operator gives you a ground state which annihilated by the annihilation operator, which is basically our from our definition, this is a coherent state. So the job is find out the superpotential part for the to find out or to construct the annihilation operator. And so, and this is psi 0, similar. Psi 0 is with the bosonic wave function, you can identify these things. So the name of the supersymmetric formalism is a justified thing. So algorithms are written in this way, that what we do, that take a Hamiltonian, which is a quadratic in momentum, and then the answers is basically gives you the thing. A is written as this way, this W is the superpotential, and if you do your calculation, then you get a Riccati equation like this, and equate it with your well-known potential part, and you get the Wx, but not easy, not so easy always, but you can do it with the harmonic oscillator, then do the problem for other potential also. I am showing you two examples of these things. And then Wx, after finding the Wx, you can construct your annihilation operator and then solve this equation, you get the coherent state. So now the example what I am doing here, this example is a little bit easier example, is a straightforward example. It's a case of a potential barrier well. So I have a potential like this, it's a constant V0. So Riccati equation looks like this for the superpotential. If we solve this potential part, you get a superpotential as a function of cot hyperbolic. And then if you dump that function in to construct your annihilation operator, and this annihilation operator acting upon the ground state, or you can say the coherent state, you finally ended up with your coherent state like this. So it's an easy one. But what we did, we use this formalism to construct coherent state for the position dependent effective mass problem. So it's a valid application of these things. It's really, people are always doing work on that particular position dependent effective mass system. So I am not going through the application part. I am just showing you some fundamental thing. I think we people doing this work in that way, it's maybe the other way around, but still I am sharing these things as because I'm telling you something which we start these things from our classical behavior so that we can get the proper quantum Hamiltonian for position dependent effective mass problem. So due to the now mass is a position dependent thing. So non-commutativity is there between mass and momentum. So the viable form of quantum Hamiltonian in case of potential position dependent effective mass is a controversial issue. So many people doing in their way, but I am now telling the way what we did. So we do the calculation, the Hamiltonian from the first principle technique. What do means that we know about that Lagrangian for the thing is when the mass is position dependent, all those things, and we can write our Lagrangian in terms of the generalized coordinate, and this n is the degrees of freedom. So we can write this Lagrangian, and when we find the supremum of this thing in sum over pi xi dot minus of Lagrangian density, we get the Hamiltonian things, which is a function of generalized coordinate and the momentum also. Now, the extremization condition which we need is basically gives you over the xi dot is pi equal to del I by del xi dot. Now there is a catch. What we use the order of xi and pi in immaterial in classical scenario, because if you write xi pi or you can write it as pi xi, it doesn't matter. But in quantum mechanics, it does. So you first redefine your pi xi dot means the this pi xi dot in this way, so that this ordering is necessary here. So you keep in mind, you just redefine your pi xi dot in this way and replace your xi dot by half of pi, and another you can replace it by pi by 1 by m classical level. So how can we do that? So just write down the Hamiltonian and with replacing that particular part, and then take the supremum, and you end with this equation. And after if you look at this equation, now position of m is interesting. So for to do the thing proper way, we adopt that we can p, we can change our p with mx dot, where x dot is changed by 1 by mp, means acted like left hand side from a m inverse type of things. We get x dot in this way, and the other for the other term we choose x dot in this way, p into 1 by m, because this two term is basically equally necessary term. So equal in footing. So that's why I'm telling you that we can change a p by this way, means x dot by this way and this way also. So if you dump that thing in our Hamiltonian, then we get our Hamiltonian looks like this. So now this Hamiltonian is gives you a extra term. If you write in your operator form, then the Hamiltonian looks like this. The extra term comes here, which is we called it as inertia term. And if you consider the mass is complex, for some physical scenario, they consider this mass is complex. So we can write the Hamiltonian in this way. So the extra term which we get here is this term. This is a very important term. We call this a inertia term. And why extra term the considered as a potential term for this position dependent effective mass problem. So why this term is generated? Because mass is always a measure of inertia, and now the measure of inertia becomes a function of position spatial variable. So every point in space is automatically mass is not in equal footing, or you can say the inertia is not in equal footing. So it turns out that there will be some balancing natural potential which can show you balance that thing. So if I go through from one point to another, so the value of the inertia change, but some natural potential is there which can balance the things and equate the both. So you can I understand in this way that this inertia term is generated due to the reason because of the inertia is now depend upon the position, and inertia is basically the measure of inertia is basically the mass. So you can say that because of the change of the inertia, or the inertia is not depend upon position, there must be a natural potential, and that potential is appear because of that thing, and this is the inertia potential. This is the potential part. Now the effective Hamiltonian, which I am writing again, and so my V effective is looks like this. The first term is comes due to the, if we differentiate, if we calculate this part, and the next part is totally dumped in, we totally dump it in our V effective, and then using the SUSY formalism, we construct our annihilation operator in that way, and then demand that A and A dagger looks like a commutation given by this, and those are the procedure which we go through that, and in that particular phi and in deformed space phi and phi, we just construct phi and phi in terms of the creation and annihilation operator, and then we find out the coherent state and try to calculate our minimum uncertainty condition, which should be applicable here, which should be there because we deal with coherent state. So we get a result like this, which is dependent upon the alpha state. So if you find out the alpha right now, so you need a particular case, means alpha is necessary to calculate these things, means the state is necessary, the rigorous form of the state. When you calculate these things, you need you have to consider a model type of things. Here we consider that mass is a function of looks like this. It's a position dependent thing, and our Vx is simple. Choose our Vx in this type of model, a potential well. And for a good solution, we just choose our nu zero values is -12, and it gives us alpha, and then we calculate the probability density and all those things. So the SUSY formalism is done here. The SUSY formalism is used here to construct the coherent state, and then we choose a particular model because to doing the calculation or calculate the uncertainty things, and we ended up with a alpha, and that gives you this is the probability distribution and all those things. So this all about our potential position dependent effective mass problem. We starting with first kind of things, we redefine our ordering thing, and then get a moment inertia part, and this inertia part is naturally occur, and after that we construct our annihilation operator and solve that equation and get the coherent state for a particular model. Now the next model, which is Lewis-Risenfeld invariant method, which I am now telling. So Lewis-Risenfeld invariant method tells you that there must be an invariant operator in the phase space. Invariant operator means satisfy this equation. So if it is, if you can prove that if this invariant operator, when it's basically there is a connection between the eigenstate of invariant operator and the eigenstate of Hamiltonian operator. So Lewis-Risenfeld method is basically applicable when we can't do that factorization in an easier way, because our Hamiltonian is a time dependent Hamiltonian. So if you do this, means you have the right hand side part is I del psi by del t type of term. So you can't do the factorization in an easier way, but you can change this problem. So in a other way, that I have you have construct a invariant operator which looks like which gives you a form like acting upon some eigenstate gives you eigenvalue and that eigenstate. So now you can factorize your this invariant operator and generate your annihilation operator. In previous things, a Hamiltonian can't be factorized, so we can't find out the uh, annihilation operator. So we just go through by this. We first construct the invariant operator, then then find out the annihilation operator. And now the construction invariant operator. Invariant operator gives you eigenstate. This phi n always gives you a Hilbert space, and this phi n and the eigenstate of Hamiltonian is both are basically connected by this phase part, means this is phi is basically this phi is the eigen vector of the eigen function of this invariant operator, and psi is the eigen time dependent Schrodinger equation solution. So you can connect these two things, just multiply this e to the power I theta and t part. And how you calculate this theta n? You just dump these things in your time dependent harmonic Schrodinger equation, and you get the equation in terms of theta, and solve it, you find out the theta. So your job is pretty simple. So you have to find out the invariant time dependent invariant operator. We construct that thing. After that, you can construct the annihilation operator, and those, and finally the annihilation operator a psi equal to 0 gives you the solution of psi is the gives you the coherent state. So now how can we formulate or construct this invariant operator? This invariant operator, as we see that this must follows this equation 35. So we have to construct the invariant operator in terms of the operator which consists in our harmonic oscillator. Schrodinger or Hamiltonian. So we use those operators to build this invariant operator. Now, we use those operators to build this invariant operator. It's practically not too easy, because consider a Hamiltonian as a function of p and x only. So you have two type of operator. One is momentum and position. Now you can construct your I in many way, that you can take p square, or you can take your p cube, or you can take px, and all the terms are there, p into x, x into p, and all those things. So what things you have to follow? That the invariant operator can be written in terms of the operator which are already in the H. So I am trying to I am writing the invariant operator in terms of all the operators which can be formed by using the operator in the Hamiltonian. And I'm writing this invariant operator in a sum over mu jt of operator oj. So now this operator O is basically formed by using the operator in the Hamiltonian, the in all sorts of combination are there. So now you have to maintain that a quasi algebra, that those operators when you calculate the commutator with H and the operator on those operators which basically help us to construct the invariant operator, we finally closed our algebra. Means the commutation always gives you the operator what we write in our invariant to construct our invariant operator. So this is a quasi algebra and it must be closed. Then only we can say that okay, they are now if the algebra we get the closed algebra, so the number of OJ as much as you take, and you must keep in mind that your algebra should be closed, and then you say that the invariant operator looks like this. So just going into a problem which is a very interesting one, that suppose a free particle problem. So free particle Hamiltonian looks like p square by 2m. Then we have to construct our invariant operator. Now the invariant operator, when you construct, we keep in mind that algebra should be closed, and you can see that the invariant operator comes out in a function of t, x, and some function of t only. So we have this invariant operator. If you try to do the quasi algebra kind of things and want to know how this particular operators are form a closed algebra, yes, this operators form a closed algebra. And now you have the invariant operator. So dump this invariant operator in that particular equation, del I by del t plus commutation of I t h equal to 0, and you end up with those values of A. Now A t is now looks like this, B t is this, and C t is simply C0 and V0. But still you have so many unknown constants are there, so you have to do it or do the calculation in any way. Do the calculation and find out the A0, B0, C0, all those things. Now, when we construct our invariant operator, now we can find out our eigenstate phi lambda. So after getting the phi lambda, we can get our eigenstate of Hamiltonian psi. This is a part where exponential term is there, is the phase part, and this phase factor, this alpha part, you can find out by using this equation. The alpha satisfies this equation, and if you do all the jobs, you ended up with this psi. People already do these things, and they ended up with this psi, and they try to calculate the delta x and delta p, and which they get always greater than equal to h cut by 2. Now, so and plot this uncertainty with time. They show that this blue solid line is basically the uncertainty of delta x, and this dashed line is basically the uncertainty of delta p with time. But the thick dotted line gives you a constant increase of the uncertainty delta x and delta p. So you can say that this is not the coherent set, but I have a point to make mention that people think that this invariant operator is a phase space operator. So it's a phase space invariant operator. So it gives you a state which is eigenstate of Hamiltonian. So this state, as this, the uncertainty of this state always increasing with time, but they still demand that this is a coherent state because of the invariant operator is a phase space invariant thing. So they construct a state which is which can be gives you you can say that this is another way to construct another concept of coherent state, but I am not so much expert on these things, and I don't give any further time in that particular thing. The another thing which I am showing you, that another example, which is Maxwell-Chern-Simons model in free falling long wavelength limit. The Hamiltonian looks like this. So again, we do the job by the technique invariant method, invariant operator formalism method. So we construct our invariant operator, and it looks like a function of px, py, x, and y, and all those things, and also a function of alpha t. Then find out all the time dependent constant. We construct our I, and then find out the psi. Those are the, and if we find out the probability, we say that these things gives you a highly localized probability, obviously for a high omega value, but it's a highly localized probability. But now I am giving you an interesting example which gives you some insight. When you construct our invariant operator, what do you mean by that quasi algebra must be closed? So take an example like this, the non-interacting damped oscillator. So you can just write this Hamiltonian in terms of J plus and J minus, where J plus and J minus write in terms of x1, x2, and p1, p2. So this, you can think that my invariant operator should be a function of J plus and J minus only. Now, if you try to close that particular J plus and J minus, you find out, or you ended up that the J plus and J minus commutation gives you a J0 type of thing. Means when you construct the invariant operator in terms of J plus and J minus and do that particular algebra, means try to calculate the commutation between this J plus operator with Hamiltonian and J minus operator with Hamiltonian, you always ended up with some extra operator type of things, which is basically as x1, p1, p1, x1 type of things. So this gives you an idea that not only J plus and J minus, there should be further terms which you have to add in that invariant operator to make that algebra close. Now, if you like look this operator, it is basically a function of J plus, J minus, and also the J0, which contain the term x1, p1, p1, x1 type of things. So just start with this, starting with these things means only the J plus and J minus, you doing the algebra, trying to close the algebra, you ended up with those terms, and this gives you idea the invariant operator should contain this term also, and this is the invariant term. So that's why I am always telling you, so construction of invariant operator is not always very easier job, because you have to do this quasi algebra, means algebra is always be closed, and when you demand that thing, you finally ended up with your proper invariant operator. Now we did these things for our position dependent effective mask problem also, but it's not a trivial one, because here we have the Hamiltonian and we pick our operator like this. So O1, O2, O3, all the things are there, and try to construct our invariant operator I, and again try to do the thing or demand that the algebra should be closed, but ended up with a peculiar thing, that O1, commutation of O1 with H, which is the first one, O1 with H always gives you a things, or there appear new operator. Same thing happens for O3 also. So O1 and O3, if we consider O1 and O3, then algebra always gives you new operator. Then you have a two path. Means you again include that operator and try to close the algebra, or you can simply ignore the O1 and O3 and try to establish a simple form of invariant operator so that the operator can satisfy the closed algebra type of thing. And yes, we do these things and we just simply ignore our O1 and O1, and there must be a thing which I am just telling you wrong thing. But okay, so if you just remove the O1, then I think O3 becomes gives you a normal thing, and we just ignore this O1 and O5. I am neglecting again because of that problem. O1, O5, and after that we just construct our invariant operator, which is now comes in terms of O2, O3, O4, O6, and O7, which already given here. O2 is X, O3 is these things, O4, O6, and O7. Those operators are there to construct our invariant operator. And then if you look at this particular term, then we stop here because we are not doing further or doing or go on with our calculation and find out our annihilation. I am just pick this example as because the necessity of closeness things means the algebra should be closed is essential to construct the invariant operator. Now after that we are doing our calculation and find out our all the time dependent coefficient things, and finally I ended up with a big enough invariant operator. That's all. So that's all. Since my talk is now, I am just concluding my talk. Thus, I am telling you about some aspects of coherent state in our the properties of coherent state and why we need to study the coherent states things. And when we study the coherent state, parallelly people always do study with the squeeze state. So I have already discussed about the squeeze states and how the things is connected in a phase space things. So we need a good thing called Wagner measure or Wagner distribution function. Then I am going our discussion discussed on the construction mechanism, so SUSY mechanisms, and apply this SUSY mechanism for different type of example or problem. In between that, one is a position dependent effective mass problem, and then the Lewis-Risenfeld invariant method and how to construct an invariant operator. And if you get the invariant operator, then you can construct an annihilation operator, and then you can construct a coherent state. Thank you. Thank you very much. So I've stopped here.
Thank you, sir. So the forum is open for questions, clarifications. Yes, Nivet, you can go again.
Sir, I have a small question, sir.
Yeah.
Sir, if you have noticed, the Lewis-Risenfeld invariant method seems a bit similar to the one we used for the converting non-Hermitian Hamiltonians to Hermitian ones. So have we tried these methods and then
No,
tried
but
for calculating?
it's really, I'm not trying at all, but if it's so, then I always try to do that thing. Since I'm not doing this thing, since I'm just doing the thing, means I'm just doing the thing, constructing the invariant operator and all those things. But you are telling that in doing this or constructing that invariant operator is as similar as try to do the non-Hermitian operator to Hermitian one. That's the thing.
Yes, sir. Yes, sir.
Also, no, I am not doing these things.
Okay, and another follow-up. Since the method is a bit similar, so
Okay.
can I take a non-Hermitian Hamiltonian, and while transforming to Hermitian, can I use the same eigenstates as a coherent state?
Yeah, actually, I am not going through that, so I'm a little bit. I'm not doing any clear answer for that right now.
Yes. Nivet, have you finished your questions?
Yes, sir. Thank you.
Pinaki Patra, you can raise your question now.
Just connection with the previous question.
You have some noise in your microphone, please.
Hello? Am I audible?
No. Noise is there, Pinaki. Hello?
Now is it also audible?
Yeah, now it is little bit audible. Please go on.
In connection with the previous question, for non-Hermitian operator, especially for pseudo-Hermitian, that is the supersymmetric Hamiltonian, one can transform it, one can use this formalism and construct the invariant operator and construct the coherent state for the same. So I think this can be done. So
Maybe you can raise your question in the chat box, Pinaki, if you want.
Yes, sir. Yes, sir.
I think Pinaki try to enlighten that point asked by Nivet, I think, but the noise is so much, so we can't understand anything.
Okay, no, okay. So is there any other question? No. I have only one question. The latter part, Lewis invariant method, you considered the algebra is linear, right? You can even consider quadratic algebra like that. Is there any work has been done in that direction by considering quadratic algebra?
Professor, I have no idea about that because I am not looking at that thing.
Okay.
I am not go through that thing, but I think I will try. If you have anything to say, because please, we are actually doing.
I'm seeing a lot of papers considering this quadratic algebra structure nowadays, so that you can enlarge the integral system.
Yeah. Also, you are trying to tell us that when we try to close the algebra,
Yeah.
so if you consider a linear kind of thing, then it is easier one. If you consider a quadratic kind of thing, it's pretty difficult, but it gives you some different scenario or some different things for study. Yeah, definitely a good point. It's definitely a good point. But in our future, we always try to do so. I think. Thank you.
So, any other clarifications, students? You need some clarifications. Okay, I'm not getting questions from students. Okay, in that sense, let us conclude the session by thanking Professor Jyoti Prasad Saha for giving a very wonderful talk on coherent states. In fact, he recalled it.
No, it is very elementary talk. Means I am
No,
trying to.
No, but it is very interesting because we are able
Thank
to
you. Thank you
recall
very much.
all
Thank
the,
you.
all the points in one seminar. Thank you. Thank you very much for giving a very, I mean,
Okay,
it will
thank
be
you.
like-
Thank you for giving me a chance. Thank you very much. Thank you.
Yeah, I will ask my students to go through your video because because all are gone for feedback to fill the feedback forms in the university.
Okay, okay. It's no problem. No problem. It's okay.
I will ask them to go through your video.
Yeah, yeah.
Really, it will be helpful for them.
Thank you, Nivet. Thank you. Thank you.
Thank you, sir.
Thank you. Thank you. Thank you. So may I leave?
Yes, yes, sir.
Yeah. Thank you. Thank you very much. Thank you, Professor. Thank you.